Okay, so now differential forms. Okay, so to introduce this idea, so first of all, let us look at the Rham complex. Of this U inside Rn, an open set. So we have some open subset of Rn, and we want to define the Rham complex of this thing. In other words, we want to define differential forms over this. Okay, I mean, in this case, I can tell you first of all what are zero forms. These are just functions. I mean, smooth functions, right? And U, so just okay. I mean, smooth functions. So this is like C infinity of U. But then there is a notation also use omega 0 of U. With this notation, omega 0 of U is used. Okay? And then what forms is just the expressions of the following form, F1 of the form. Okay, so omega equal to F1 dx1 plus F2 dx2 plus Fn dxn is Fi belonging to C infinity of U.
This is one forms.
These are one forms, yeah. And okay, I mean, just define, okay, then two forms. These are expressions of the form omega equal to sum Fij dxi wedge dxj. Okay, so I summation over I and j, Fij are smooth functions. And there is a rule here that we have to observe, namely dxi squared is equal to 0, and dxi wedge dxj is equal to minus dxj wedge dxi.
What is the wedge? Is it just a symbol?
It's just a notation now, but that doesn't matter. You can define it in more complicated ways, but at the end, then that's what you have to remember. So I tell you the end result, actually, what you need. So this is kind of practical, what's it called? Working definition. So, or a poor man's definition of differential forms, if you.
So that thing is just the dimension that we're working on, right? So if we're working in R2, then we have like two.
Yeah, exactly. So, and then you just keep going. And then what is an N form? Finally, an N form is just expression of this form, omega equal to F dx1 raised to dx2 raised to dxn. Okay, so this is the rule. It should be negative. So then we just put them inside some complex. We want to form a complex here. Like that. And we want to define these maps. So we call these maps, I will define them, I call them D. There is D. There is D. So how do we define this map? Well, I mean, the map is extremely easy to define. The map is like this. Basically, D of, if you have some K form, F E X I1 wedge D X I2, ik is equal to d of f wedge dxi1 wedge dx ik.
What is D of F? It's just a differential.
Yeah, now I define, yeah, exactly. I define d of f equal to sum df dxi and then dxi. I from 1 to 2. And you extend it by linearity. Okay. So we have it. This is called the Rham complex. Now you, okay, so I mean, using this, you can extend it to everything.
And if it's a sum of different terms, the D acts linearly on the sum.
Yeah, extended by linearity, exactly, as I said, yeah. So now there's a little lemma you just prove that D composed with D is equal to 0. Thanks to these sign conventions that we have. So let me check this, for example, in the case of some special case. I mean, that this is quite straightforward. I mean, this is a consequence of proof. This is a consequence of the partial derivatives in different orders commute to dxi. It's a result of that. So let's look at some example just so that maybe this this looks natural to you. So let me take I don't know, n equal to 3 maybe. Okay. So let's take a one form f dx plus g dy. Okay, so f1 dx1 plus f2. No, I just want to use more pedantic notation. F dx plus g dy plus h dz. Let's compute d omega. So what is d2 of omega, for example? That's equal to d of omega, right? Okay. So what is that? So now what is d of omega? To compute d of omega, we just do df. Okay, so this is df wedge dx, right? Plus dg wedge dy plus dh wedge dz, right? So now, but what is df? Df has 3 terms, right? When you multiply, the dx term cancels because dx wedge dx is 0. And so this is equal to d of, so df dy, okay? Then you have got dy plus df dz, and then wedge dx plus this one, right? So now what you do, you just then let's do d of this. Okay, so we've got d of, for example, df dy. Okay, then dy wedge dx, dy wedge dx plus goes on. Now what is d of this guy? If you want to compute d of that guy, you're going to get, okay, so you're going to get 3 terms. So you're going to get d dx, I mean d2 dx dy of f times dx plus d2 f. I just take this with respect to dy. dy wedge dy yeah, no, that's okay. dy wedge dx, dy wedge dy dx plus d2 f dz dy dz wedge dy wedge dx plus zillions of other terms. I don't write for now. Okay, so first of all, you notice that this term is zero because dy wedge dy is zero, so this is zero. And then okay, so this dx, I made a mistake here. This is dx, dy wedge dx. And this term is also zero because there are dx appearing twice here. So finally, what happens is that for each term, like d2f, dz, dy, dz, wedge dy, there is a term which you're going to find it over there, which is of this form, d2f, dy, dz, and then I've got dy, wedge dz. And these terms cancel each other. So let me put it like this, plus this. You see, because these two terms have negative sign, but these two terms are positive. They're equal. So basically, what the reason for d2 equal to 0 is the following. There is anti-commutativity for differentials and commutativity for derivatives. They work together to cancel. Anyhow, so you can write a formal argument, but all boils down to this theorem, which is called, when I was teaching calculus, I read in my calculus textbook that this is called Clairaut's theorem. Yeah. But I think any mathematician before Clairaut knows this. It's just a matter of, because textbook writers want to attribute things to make it more easier to memorize.
Was he the first person who proved this, or was it like rigorously proved?
His proof certainly was not rigorous. I can bet, because he was in 18th century, mid 18th century. But they had all the idea. They had all the idea correctly. Euler knew this. I mean, I would give my head if Euler didn't even. But maybe he wrote a proof. Anyhow, so this is this. Okay, so this is called the Rham complex. Now, so what we need is the Rham cohomology now. So okay, so let me just write the Rham complex again. So again, so we just write omega 0 of u, the of 1 of u, and u. So so there is some definition. So these are called closed forms. So omega belonging to omega k of u is called closed if its differential is 0. And then we have idea of exact forms. It's called exact if there is a k-1 form whose d is this one. The eta, for some eta in k-1. And of course, d squared equal to 0 implies that exact forms is a subspace of closed forms, right? Exact forms.
Sorry, what's theta?
Huh?
What's theta?
Oh, eta is some form in omega k-1 of u. Because d increases the degree, right?
Mm-hmm.
Okay, so d squared equal to 0 exact, inside closed. And of course, this is all inside omega k of u. And there is even some notation here. So I believe notation is called bk of u inside zk of u inside omega k of u. And when you divide this subspace, but that subspace is called the Rham cohomology of u. Okay, so definition. HK the Rham of u is just the quotient of zk by bk. So this looks like a nonsensical game, except for the fact that when you do this, you detect topology of U. So dimension of this space is exactly k-dimensional holes inside the space. So that's what that's what the Rham's theorem say. But let me just so this is the Rham cohomology. Do you have any questions so far about this?
Is there a intuitive relation between like forms and differentiation? Like because in calculus, there is for like multivariable functions, we just write them in forms and think of dx and dy as very small.
Yeah, this is exactly what it is. Yes, but to do the algebra, I won't talk about those things. But it's exactly these are infinitesimals. Yeah.
So
the x squared is like infinitesimal of order 1. If you raise it to power 2, it becomes 0. And then dx plus dy is also infinitesimal. If you raise it to power 2, you get the law dx dy is equal to minus
there's
dy.
like a very complex subject, right? Man, something like think of the dxi as something very, very small.
Yeah, you can think of it like that. But I mean, so what there is also relation to singular chains and cycles through integration, which we'll use it soon. But now let me just give you maybe just one example okay, so I don't know, should I give you an example of this? Why this kind of detects homology? I mean, cycle holes or something. Maybe I just give an example. So here's an example of 2 dimensions. R2 minus 0 punctured the plane, right? Punctured plane. So let me get omega belonging to omega 1 of u. I want to define an omega here, which is closed. The omega is 0, but is not exact. But not exact. Do you remember this from calculus? This is multivariable calculus, nothing but that. A one form which is closed but not exact.
Like x over x squared plus y squared minus.
Yeah, it's exactly, it's that one. But that one has a meaning, has a geometric meaning, which we discussed actually. Huh?
Cool.
Huh?
Cool.
But I mean, it's something much more elementary. It should be in Euclid even. That concept. The concept that I told you I hated.
Yeah,
Huh?
Yeah.
No, okay, that's one of them. No. In my long list of things. Sorry. No. There's something else. It's angle. So here is something like a magic. It's really like a magic. Angle is not defined, but its differential is defined. So this omega is d theta. So what is theta as a function of coordinates? Is tangent inverse of y over x, right? So this is a badly defined function, y over x. I mean, first of all, tangent is an inverse of a periodic function. Ooh, it's terrible. And then this is y over x. I mean, you have to cut the whole line x equal to 0, make it. And so there are all kinds of problems with this. But let's compute this differential. So what is it? This is like tan inverse of y over x with respect to x dx, right? Plus tan inverse of y over x with respect to y dy, right? That's our first definition. Now let's look at now what happens. So let's look at it. I mean, what is that? What is the derivative of tan inverse? You're a student, you're supposed to know.
1 over 1 plus x.
1 over 1 plus x squared. Okay, so is it, well, no, but
No.
tan inverse of u is u prime over what? 1 plus
We apply the same.
u prime over 1 plus u squared? Is that what it is? Okay, so you so yeah, you're right. Yeah, so this is like y over x divided by 1 plus y over x squared, right?
What do you mean y over x?
Oh, these are partial derivatives.
Okay,
Yeah, dx plus, and then y over x y over 1 plus y over x squared dy, right? So let's see what we get, what Rayhan said. You're getting what you said, I think. So what is that guy? That guy is equal to minus y over x squared, right? Over x squared plus y squared over x squared. Dx plus 1 over x. Ooh, yeah. That doesn't look good. So, I don't like them. 1 over x. No, that's okay. 1 over x. 1 plus y2. Okay, x2 plus y2 over x2. And this is dy, right? So let me simplify this now. So omega then equal to, okay, so here is
Minus y over.
minus y over x2 plus y2 dx plus x over x2 plus, it's what you said, right? Plus x over x2 plus y2 dy. So this one form is the differential of the angle, but you see, now this belongs to omega 1 of R2 minus 0, of course. Right. And it's closed. Why? Why is it closed? Well, I mean, there is a direct way. You just take the differential and show that, okay, by brute force, this differential is 0. But there is also a more enlightened way to say that, hey, this omega is d theta after all. But this theta doesn't really exist. It's like a ghost. But it's d theta, and then you're taking d of d theta, so d2 should be 0. So intuitively, it should be 0. No matter what is 0, it's close. But now I claim that this is not exact. But not exact. So why it's not exact? So in other words, you have to show that there is no function f of x and y such that omega is never differential of a function f belonging to C infinity of R2 minus 0. I mean, there is a good way to do this, namely integration. You just show that its integral over S1 is different from 0. But I mean, to do this, I have to introduce. But that's exactly what we do in calculus. Did you take calculus with me?
Not calculus.
Advanced. You didn't take advanced calculus. If so, you didn't learn this then. I think most probably you didn't learn this. Did you learn this? In advanced calculus?
No,
You should have. You should get your money back. Really? No. No, you did extremely well, of course, but I mean, usually they don't emphasize enough the importance of these things in advance in multivariable calculus. Anyhow, so this is something, and actually with little bit of work, you can show that this dimension of H1 is 1, and that's a generator. So dimension of H1 Rham of R2 minus 0 is equal to 1. And this omega is the generator. So you can think of all of this Rham cohomology as a generalization of this sort of things that we're doing here with one forms and stuff. Okay. So I mean, I can give you two-dimensional examples and three-dimensional examples, but there's no point. So I can answer question if you have that later. But now, if you don't have a question, so I'll tell you how to do this over manifolds. That's much more interesting to go over manifolds. That's not so trivial, right? So how to define forms on manifolds, I mean differential forms on manifolds. So this is the thing we have to. So there are different ways to do that. We have different approaches. One approach, which is kind of, so the idea, we define it in coordinate charts, but then we make sure that they are compatible. So define over coordinate charts plus compatibility. So I have to give you what the idea is, and then we'll. So to do that, we need a little bit of things. So recall. So we have this idea pullback of differential forms. In other words, imagine you have a function f from u inside Rn to some v also inside Rn. So this is a smooth map, imagine. Okay. Then the pullback, you can define it like this. I mean, this is a very important operation. It's kind of functoriality here. So the pullback is the following: f star, f upper star, pulls forms on the target to forms on the domain. It goes in a different direction. That's good. So it goes from omega k of v to omega k of u. How does it work? So imagine omega is of the following form: f b x I1 h b x ik. Okay, I mean, for that reason, I'm gonna introduce this notation d. Just I use y coordinates. Yeah, okay. I'm gonna use. Okay, so let me just for now it's okay. Oh, f is pretty bad, so this is called h. It's really terrible. Yeah. The variable of a function and the functional cost. So what is f star of omega? F star of omega, something you want to be something on u, right? So here I just compose this is equal to h of f, mean composed with f, right? H composed with f. And then this is D. I just put F(I1) wedge D F(I)k. But remember this F that goes from U inside Rn to V inside Rn. So I'm just writing its coordinates as F of whatever Y is equal to F1 of Y, F2 of Y, Fn of Y. It has n coordinates, right? So, I mean, this is like your x1, this is like your x2, this is your xn. You just replace these things here. As it pull back. Okay. Okay, so I mean, this is something that if you have seen differential geometry, you have seen it, or maybe in some topology of differential forms also you have seen it. So this, but anyhow, this is the definition. So there are two nice properties of this. One property is that this commutes with D. F star commutes with D. So F star of D is equal to D composed with F star. Again, this is just some functoriality. And the second property is that F star of omega wedge eta is equal to F star of omega wedge F star of eta. So basically, F star is an algebra map. So F star from omega so now, okay, so you can think of it as direct sum of omega k of V over Rk to direct sum omega k of U is a graded algebra map. Is an algebra map plus morphism of complexes. I mean, this preserves the differential chain map. I mean, to be formal, I should say co-chain map because the differentials are increasing, but that's okay. That's what we need about this behavior of F on the, I mean, pullback, behavior of pullback. So now using this idea, I can move everything to over manifolds in the following way. Any questions? You have a question? No. Okay. Good. So now let me then see how to move over manifolds. So in other words, so let M smooth manifold. So we want to define omega k of M. Of the dimension of M. So what is this omega k? K dimension, k forms on this. So I can define it like this. I mean, so definition. A K form, maybe I just say smooth K form. The smooth K form is a choice of a smooth K form on each coordinate chart, for each coordinate chart. So remember what was a coordinate chart? The coordinate chart was a map, phi, we use the word phi, or the letter phi, from U open inside M, right? To phi of U, right? Open. So let's call it V. This is open inside Rn, right? So this omega of this chart U and phi belongs to omega K of V. There we go. Is a choice of a K form on each chart such that, I mean, the compatibility now comes into the picture, such that for any two charts, U and phi and U prime. Okay, so U prime, phi prime. Okay, phi prime is a bad idea. Maybe U1, phi 1, U2, phi 2. So if you do that, you get this map, right? You get phi 2 inverse composed with phi 1 from V2 goes to, I mean, from phi 2 of V2, so phi 2 of U2. Okay, U1 intersection U2, so U1 intersection U2 to phi 1 of U1 intersection U2. So let's call this map maybe, I don't know, maybe phi 1, 2. We should have actually in this case, so because this is inside inside this V2 thing, so we should have phi 1, 2 star of omega B and psi. It should be equal to omega U and phi. So we make sure that everything is compatible. So let me draw a picture maybe that will give you an idea. So here is your manifold, right? So we have two charts, U1 and U2.
Wait, what side?
Sorry,
What is side?
what is psi?
Yeah.
Oh yeah, I'll tell you what psi is. Oh, actually, I should. Okay, so let me be. No, I should use phi 1 and phi 2. Actually, that's a good. So this is U1, phi 1. This is U2, phi 2. I will fix it in a second. I'll fix it in a second. So here is phi 1. This is phi 1 of U1. Okay, and here is phi 2. And here is phi 2 of U2. This is the intersection, and they come here, and this is here. Okay, so if I just take phi 2 inverse, this is phi 2 inverse composed with phi 1. And this, I believe I called it phi 1, 2. Oh, no. I don't want to do that. I don't want to do that. I want to go here, actually. I mean, it doesn't matter. I can invert it actually. So well, let me take that. Yeah, that's okay. So this is phi 2 inverse composed with phi 1. So what you're saying is that, look, I mean, you have a differential form here, you have a differential form here, and it's such that if you restrict it to these relevant domains, the pullback of the differential form here should be the differential form here. That's it. It's a compatibility condition. That's so you can define, you can actually say this is a contravariant functor from this set of, from the category of open subsets of these or domains of charts to the category of I don't know, the wrong complexes on open subset of Rn, something like that. It is really a contravariant functor. That's it. Just for that, for your category theory, that there is some use for category theory. Yeah. But I don't know what is the homotopy type theory. How to define it there. Yeah, I mean, when there's no isomorphism, then that's just isomorphism means equality, right?
Yeah.
Can you imagine that world where there's no isomorphism? Everything, the two things that are isomorphic are actually equal. That's really very, very, very restrictive. You're policing mathematics now. You don't want people to make mistakes.
I think the people from homotopy type theory think it's more the opposite. It's like, if rather than restricting, it's expanding.
Oh, is that right?
Yeah. They're not restricting the notion of identity, they're extending it.
You're extending it. You're extending it.
Isomorphism.
Oh, by that you're extending.
Yeah, and that's what.
That's what they say. Well, that's a good. Yeah, do you agree?
Also, forms are still open though.
Forms are not done.
No.
Oh, there's a problem. You should take it for the assignment. Oh, that's interesting topic then. We should discuss it next. Forms are not done in homotopy in hot. Okay. So with this we can define forms and we can define so now I just say that then I'm just going too fast, but you see the ideas. Of course, omega 0 of m. What is omega 0 of m now? Now here's something actually to think about. What is omega 0 of m now?
All the holomorphic functions.
No, there's no holomorphic function yet. We are over a smooth manifolds.
Smooth functions.
Yes.
Yeah, exactly. So I define it by coordinate charts, all these things are stupid things. But then in the case of functions, these are just smooth functions. Because it's like defining a smooth functions to be this coordinate, but the compatibility means that there is well defined if you just define it in one coordinate. So this is really C infinity of m. Omega 1 of n, I cannot show you an object which would be very easy to explain in terms of calculus terms. But I mean, this is just in terms of this coordinates. It's like a big bag of coordinates, and then there is a differential form each coordinate. So you just come with your one form, and it's omega 1. And there's of course D also makes sense. You can go over there D. And then there is omega n. Let's see. So that's for now. And honestly, for this course, we really need n equal to 2 surfaces. So we have only this omega 0 of x, omega 1 of x, and then we have omega 2 of x. Now, one thing that's important to notice is that I did everything. You didn't ask me what a smooth function means, or is it real valued or complex valued, the smooth function. You didn't ask me.
Doesn't it mean that it's got infinitely many derivatives?
Yeah, infinitely many derivatives. That's what I was thinking. I was talking about the value of the function. Is it real valued or complex valued? You didn't ask me, or maybe somewhere else. You have the option. You can take real valued functions or complex valued functions. Now we are going to take, if you take complex valued functions and complex valued forms, then usually people put this. And that's what we need actually in Riemann surface theory. Okay, so be careful when we write these complexes like this. These are all complex forms. It just means that the coefficients are complex valued functions. Okay, now what happens that if X is a Riemann surface, we notice that we can decompose this into two parts in a canonical way. So this is the punchline actually. Then omega 1 C of x can be decomposed into the dx sum of two parts called omega 1 0. So these are called 1 0 type forms, and these are called 0 1 type forms. Okay, so now, so our next job is to understand such forms now. Okay? Okay, again, to understand this decomposition, we first understand it on open subsets of the plane, of the complex plane, and then we will tell you what happens over Riemann surfaces. Any questions? So the whole thing now is to understand this decomposition. Okay, so now we are going to define that. So over open subsets of C, open. So usually you write a one form in the following form: f of xy dx, right, plus g of xy dy, right? Now we are going to introduce two one forms, which are the following form: dz. So let dz equal to dx plus I dy, and dz bar equal to dx minus I dy. Okay, so are you troubled by this dz and dz bar? There's a psychological thing which sometimes I know by experience it bothers a lot of people actually. They say, what is dz, what is dz bar? But as one forms, you can see this is a one form and this is a one form. There's I and there's minus I. It's a combination of one form, and it's completely okay, right? So using this, of course, then you see that dx is equal to, if you add these two things, equal to 1/2 dz plus dz bar, and dy is equal to 1/2 or 1/2i, I'm sorry, dz minus dz bar. Okay. So now we just say so then any omega. So any one form omega belonging to omega 1 of u, you can write it as some function a of xy dz plus another function b of xy dz. You can just replace dx by this and dy by this and compute a and b in terms of f and g. We can write it. Okay, now question. Okay, so now what you can do? So now I can define what is a 1-0 form. So definition.
dz bar.
Question, yeah.
dz
Oh,
bar.
dz bar. Thank you. Yeah, excellent. Thanks. So definition. A 1-0 form on U is a one form of the form omega equal to a of xy dz. it's only of this form. There's no dz bar component. You can do that. I can define how I define. And a 0, 1 form omega equal to, I don't know, I just write E of x and y. dz bar. So this is of this form. This form. Okay. Now let's look at also do all of this these bars. So we just defined the operator d dz. This is 1/2 d dx. Okay, 1/2 d dx minus I d dy. And d dz bar equal to 1/2 d dx plus I d dy. Okay. So these are the two differential operators. If you want, these are also vector fields because they are defined in terms of this basis vector fields, but they are of this form. I mean, the point of these things is the following result, which is you can write it Cauchy-Riemann equations. It's a simple lemma, so let me write it. F belonging to C infinity of U is holomorphic if and only if d dz bar of f is equal to 0. So this something is holomorphic if it is in the kernel of this operator d dz bar. So what does this mean? We know that in terms of differential operators, something is holomorphic if and only if it is a solution of Cauchy-Riemann equation. So basically, this dz bar is called Cauchy-Riemann operator, and in fact, the kernel of Cauchy-Riemann operator is exactly holomorphic function. So this is proof. Use CR equations. That's it. Okay, yeah, I highly recommend you write this down for yourself. Write down Cauchy-Riemann equations. And you notice that that's not the way you should think of Cauchy-Riemann equations, the way that it's taught in undergraduate classes. That's the wrong way to think about it in terms of these two equations. In some sense, is wrong way. The right way is this. I tell you why. Any function you can write. So any smooth f of xy, you can write it f of xy as a function of two variables z and z bar. Right? But I mean, okay, so what is it? Z is equal to x plus iy. Z bar is equal to x minus iy. So again, if you add them, you get x is equal to 1/2 z plus z bar, and y is equal to 1/2i z minus z bar. So you notice that any function, you can write it as a function of z and z bar. So Cauchy-Riemann equations that says d dz bar of f equal to 0, it means that this function has no dependence on z bar. It's only a function of z. And z is the holomorphic variable.
What if,
So that's the right. And actually, if you open Riemann's thesis, 1851, in the first line, he says, he writes this equation, not Cauchy-Riemann equations. That's the way they were thinking, and it's the right way, of course. It's only a function of z, not z bar. And if something is a function of z bar, it's anti-holomorphic, which of course exists. any polynomial in Z bar is anti-holomorphic. Z bar to the power n, for example, is an anti-holomorphic function.
What do we mean by depending on Z bar? Because if we know what Z is, we can uniquely determine what Z bar is, right? So what do we mean exactly by?
No. Your function is not only a function of Z, it's a function of X and Y.
Right.
So if you know Z, so you have to be able to replace those variables by the given variables in that term. So yeah. Okay, so now what else is remaining? Okay, so then, so now what about two forms? I just, if you give me a second, I will finish with two forms and then we go. So again, similar. So what happens for two forms? On U, so this is omega 2 of U. Okay, so a two form we can always write as omega equal to f dx wedge dy, right? But now let me write for dx and dy in terms of dz and dz bar, see what happens. Dx is equal to dz plus dz bar, divided by 2, right? And dy is equal to, sorry, I'm going to be done in a second. 1 over 2y dz minus dz bar, right? If you put these values, dx and dy, into this equation, you get something in terms of dz and dz bar. So you get this is equal to 1 over 2i f dz wedge dz bar. Because dz wedge dz is 0, dz bar wedge dz bar is 0, and you have got here dz wedge dz bar and dz bar is what they just give you. And there is this, yeah. Okay, that's it. I don't want to say more because you're really stretched today. So I'm sorry for. So thank you for your patience. And so we did cover good deal now. So where is this?